Hello, we are Zach and Brianne, and we are going to discuss categorizing journal articles. I'll start us off with an introduction to the data and the project, and we'll then turn the time over to Zach to discuss the topic modeling and classification modeling. Then I'll close out the presentation with some recommendations. We are taking this approach from the view of academia-based individuals and their needs for research articles and publication. We hope that through this application, relevant articles based on topic modeling can be more easily found through looking at keywords and titles and abstracts in relation to the established topic model. Additionally, which is our main point, is we hope to improve the efficiency of finding appropriate journals for your articles by classifying articles based on titles and abstracts to a specific topic. Then you can look to see what journals are popular in that topic. This also has an advantage because you'll see the keywords that are popular in the topic, so you can improve your own keyword list as needed and as appropriate. And this will help others find your article for citation purposes and knowledge spreading. We used an API to gather data from Archive, the open access archive from Cornell University, of scholarly articles in physics, maths, computer science, quantitative biology, quantitative finance, statistics, electrical engineering, and economics. To obtain a select amount of data, we utilized 21 keywords and a limit of extracting 20,000 entries for each keyword. The keywords went from the general terms like graph and colorization to more specific terms like physics and unsupervised learning. Interestingly, 7 of the 21 keywords we used reached the limit of polls. They were transformers, graph, colorization, attention, explainable, molecule, and physics. Additionally, the term semi-supervised learning, with the hyphen between semi and supervised, did not go through any iterations. This could be that the database didn't have any articles with this term, or that it was spelled without the hyphen, so was therefore unrecognized by the code. These keywords and the limits we set brought the overall article count down from over 2.2 million potential articles to 64,573. We focused on just obtaining the title, abstract, and terms, or the topic of these, and that took about an hour to process. Initially, we thought the term data would be helpful, but some of the articles were classed into 11 terms or topics, which made developing models overly complex, so we decided to ignore those data points. So like I said earlier, we have 64,573 articles. However, we did some exploratory data analysis and found that there were 14,237 duplicate titles. We elected to remove these as they were either very similar articles by different authors who titled them the same, or there is a chance that the archive doubled up on an article. After removing the duplicated titles, we had 50,336 articles. Of these, there were 2,907 title terms that only occurred one time. There were also only 3,961 unique terms in the titles. The next step was to prepare the data by normalizing and tokenization. To normalize the data, we utilized functions from Categorizing to normalize hyphenated words, quotation marks, and Unicode. We also used Categorizing to remove accents. Next, we used the string library to remove English stop words. To tokenize the data, we split on white space and made all the text lowercase. And finally, we had to undo some of that because some of our application needed to be in the form of a string and not a list of tokens. So the list of tokens was detokenized to form a string for those applications. Next, we performed some rudimentary descriptive statistics to find the number of tokens, the number of unique tokens, the number of characters, average token length, and the lexical diversity in the titles and abstracts individually as well as them combined. Titles typically had longer average token length at 8.1 compared to abstracts 7.6. This is probably because abstracts are full sentences while titles are typically just one sentence getting the main point across. Titles also had a higher lexical diversity at 0.067 than abstracts did at 0.017. We also looked at the top 5 common tokens in titles, abstracts, and their combination. Titles and abstracts had very similar results in the top 5 common tokens in that they were heavily populated with data science terms. Specifically, titles were dominated by learning, detection, deep, neural, and networks, while abstracts were dominated by learning, data, model, methods, and models. To help visualize our findings of preliminary descriptive statistics, we developed word cloud plots of titles, abstracts, and combination of titles and abstracts. From these, you see the heavy influence of data science terms, which could impact model performance down the line, as we will potentially have an imbalance of topics, with most articles going to data science topics instead of topics like finance, physics, or biology. I'm now going to turn the time over to Zach to go over the next phase of the project.
Thanks, Brianne. In the following section, we will delve into the methodology we employed for our project. Initially, we took measures to normalize and clean our data to ensure accurate analysis. Subsequently, we experimented with multiple topic modeling algorithms to establish discernible journal categories. Once we have completed this stage, we partitioned our data into separate test and training sets. Our training data set was then utilized to train our classification models, while our test set was allowed us to verify the accuracy of our predictions. Finally, we evaluated the outcomes of our models to gain a comprehensive understanding of our results. Let's go into each step in more detail. The first step we had to take after cleaning and normalizing our data was to develop our categories using topic modeling. Topic modeling is a technique in natural language processing, NLP, that involves identifying and extracting the underlying themes or topics in a collection of text documents. Topic modeling is an unsupervised learning approach that allows for discovering the latent patterns and structures in large corpora of text data. The goal of topic modeling is to identify a set of topics that can capture the main themes and ideas present in the corpus, and to determine the distribution of these topics within each document. Typically, topic modeling involves representing the documents as a bag of words, TF, IDF, or word embeddings, where each word is treated as a discrete variable. The technique then uses statistical models to identify the latent topics that are most likely to have generated the observed word distributions in the corpus. Topic modeling has several advantages in NLP. It allows for automated discovery of the main themes in a corpus of text data, which can be used for various downstream tasks such as document classification, summarization, and visualization. Topic modeling can also help identify latent patterns and structures in text data that might not be obvious to human readers. In doing the topic modeling step, we limited the number of models we tried to 3: non-negative matrix factorization, latent semantic analysis, and latent Dirichlet allocation. Let's review our results of each one. Non-negative matrix factorization in MF is a popular unsupervised learning technique that factorizes a non-negative matrix into 2 non-negative matrices of lower rank. The goal of NMF is to learn a low-dimensional representation of the original data that captures the underlying structure. The technique has been applied in various domains, including image processing, text mining, and bioinformatics. NMF has several advantages over matrix factorization techniques, including the ability to handle non-negative data and the interpretability of the resulting factors. The resulting factors represent a linear combination of the original features and can be interpreted as meaningful patterns or topics in the data. The performance of NMF depends on several factors, including the choice of the number of factors and initialization method. The number of factors should be chosen based on a specific problem and the complexity of the data. The initialization method can also have a significant impact on the results, and several techniques have been proposed to improve the quality of the factorization. Upon application of NMF to our data, we observed the emergence of well-differentiated topics that were distinct from each other. Additionally, these topics exhibited a high degree of cohesion, suggesting tight categorization. Moreover, the distribution of documents across the generated categories was moderately balanced. Overall, we were impressed with NMF's performance in generating topic categories from our corpus. Next, we tried latent semantic analysis. Latent semantic analysis is a technique used in natural language processing and information retrieval to discover latent semantic relationships between words and documents. LSA works by representing documents and words as vectors in a high-dimensional space and then applying a matrix factorization technique, such as singular value decomposition, to reduce the dimensionality of the vectors. The resulting low-dimensional vectors can be used to represent the semantic content of documents and words and can be used for tasks such as document classification, information retrieval, and question answering. The technique has been applied to various domains, including text mining, sentiment analysis, and topic modeling. Upon application of LSA to our data, we did observe the emergence of well-differentiated topics that were distinct from each other. We also saw that these topics exhibited a high degree of cohesion, suggesting tight categorization. However, the distribution of documents across the generated categories was moderately unbalanced. Therefore, we were not impressed with LSA's performance in generating topic categories from our corpus. Lastly, we tried latent Dirichlet allocation. Latent Dirichlet allocation, or LDA for short, is a popular probabilistic generative model used for topic modeling in natural language processing. LDA represents documents as probability distributions over latent topics, where each topic is a probability distribution over words. LDA assumes that each document is a mixture of several topics, and that the words in each document are generated from the corresponding topic mixture. LDA has been successfully applied in various domains, including text mining, sentiment analysis, and recommendation systems. The results of LDA can be evaluated using metrics such as topic coherence and perplexity, and can be visualized using topic models. The advantages of LDA include its ability to identify latent topics in text data, its scalability to large datasets, and its interpretability. LDA can also handle noisy data and can be adapted to different domains and languages. However, LDA has several limitations, including the difficulty in selecting the number of topics, the sensitivity of the initialization method, and the inability to handle dynamic topic modeling. Additionally, LDA assumes that each document is a mixture of topics and may not be suitable for all types of text data, such as short text or highly specialized domains. After applying LDA to our data, we found that the algorithm did not produce clearly differentiated topics that were sufficiently distinct from one another. Additionally, we observed that the distribution of the documents across the generated categories was moderately unbalanced, with the majority of the documents being assigned to Category 1. We suspect that the specialized nature of the journal articles in our corpus may have contributed to the underperformance of LDA. Unfortunately, we were not satisfied with the results of LDA in terms of generating meaningful topic categories from our corpus. After reviewing the results of all of our topic models, we decided to do our classification modeling with the results of our NMF categories. Here is the NMF topic model word cloud for each of the categories developed. A topic model word cloud is a visualization technique used to represent the most frequently occurring words in a given topic or set of topics in a topic model. Word clouds are graphical representations where the size of each word is proportional to its frequency in the topic or set of topics. To create a topic model word cloud, the words associated with a particular topic or set of topics are extracted from the output of a topic modeling algorithm. These words are then ranked by their frequency of occurrence within the topic or set of topics. The most frequently occurring words are then displayed in the word cloud, where the size of each word reflects its frequency. Topic model word clouds are often used as a quick and easy way to understand the main themes or topics in the corpus of the text data. They can be used to visualize and summarize the content of the set of documents or to identify key terms that are frequently used within a particular topic. Topic model word clouds can also be used to compare the topics generated by other models or to track changes in the topics over time. However, it is important to note that topic model word clouds have limitations. They do not provide a complete representation of the topics or the underlying relationships between the words in the topics. Additionally, the word clouds can be influenced by the choice of stop words and pre-processing techniques used in the topic modeling process. As you can see, the categories generated from our NMF are pretty good, but they are not perfect. There are still opportunities for improvement doing things like customized stop word lists or adding n-grams and potentially using lemmas to address word stemming issues we see in the cloud. Now that we have NMF categories, we then moved on to build our classification models. Classification modeling is a supervised learning technique in machine learning that involves predicting a category, label, or class for a given input data point. The input data point is typically represented as a set of features or attributes, and the classification model is trained on the labeled dataset to learn the relationships between the features and the target labels. The goal of classification modeling is to learn a mapping function between the input features and the target labels, which can then be used to predict the class of new unseen data points. Classification models can be trained using a variety of algorithms such as decision trees, logistic regression, support vector machines, and neural networks. We only tried two models, multinomial logistic regression and multinomial naive Bayes. Let's review each of them in more depth. The first classification model we tried on our data was multinomial logistic regression. Multinomial logistic regression is a popular method for text classification that extends binary logistic regression to handle multi-class problems. In text classification, the goal is to classify a document into one of several predefined categories based on its text content. Multinomial logistic regression is often used because it can handle the high-dimensional and sparse nature of text data and provides a probabilistic framework for classification. In multinomial logistic regression for text classification, the input of the model is a set of features or attributes that represent the text content of the document. These features can be various text-based representations such as bag of words, TF-IDF, or word embeddings. In our case, we use TF-IDF measures. The target variable of our multinomial logistic regression is the class label of the document, which is represented as a categorical variable with multiple levels. The model estimates the probability of each class given the feature values of the document using a set of regression equations, one for each class. The coefficients of the regression equations are estimated using maximum likelihood estimation, and the model is optimized to minimize the negative log likelihood function. When a new document is presented for classification, the model calculates the probability of each class given the feature values of the document using the estimated regression equations. The class with the highest probability is assigned as the predicted class for the document. Multinomial logistic regression is a popular method for text classification because it can handle high dimensional and sparse data, provides interpretable coefficients that indicate the importance of each feature for each class, and can easily extend to handle new classes or features. However, it may not perform well when classes are imbalanced or the features are highly correlated, and regularization techniques may be necessary to prevent overfitting. The results of our model were great. The overall AUC ROC score was 0.963. The AUC score tells us how efficient the model is. The higher the AUC, the better the model's performance at distinguishing between the positive and negative classes. An AUC score of 1 means the classifier can perfectly distinguish between all the positive and negative class points. The last model we tried on our corpus was multinomial naive Bayes. Multinomial naive Bayes is a probabilistic classification algorithm based on Bayes' theorem, which assumes that the probability of a particular class is dependent on the probabilities of each attribute value given that class. It is commonly used in natural language processing and text classification tasks where the goal is to classify a text document into one of several predefined categories. Multinomial naive Bayes is called multinomial because it assumes that the attributes or features are represented as counts or frequencies, such as the frequency of occurrence of each word in a document. The algorithm works by first estimating the probability distribution of each feature for each class based on the training data. Then, when a new document is presented for classification, the algorithm calculates the probability of each class given the document's feature values using Bayes' theorem. The class with the highest probability is assigned as the predicted class for the document. Multinomial naive Bayes is considered a naive algorithm because it makes the simplifying assumption that the features are conditionally independent given the class, which means that the presence or absence of one feature does not affect the probabilities of the other features. This assumption is often violated in real-world data, but the algorithm still performs well in many cases and is relatively fast and efficient. The results of our multinomial naive Bayes model were terrible. The overall AUC ROC score was 0.834, but several of our categories had AUC scores that were no better than guessing or flipping a coin.
Zach, to reiterate what Zach just said, we recommend using the non-negative matrix factorization or NMF model to generate topics, since that model was able to fill topics in a way that made sense. By this, we mean that the NMF topics were separate from each other, filled with similar terms, and had a sensible spread of articles in the different topics. In order to classify documents into categories, the logistic regression model is the best when utilizing the categories developed by the NMF model. And the choice and classification model is validated in the high AUC ROC values present in not only the overall test data, but in each individual category, compared to the scores of the naive Bayes model. Going forward, if you would like to implement the model as is, we recommend using the established logistic regression model that utilizes the non-negative matrix factorization topic model for topic formation. However, there are many options for improvement that stem from the data gathering step up through the modeling steps. Text cleaning can be improved by removing jargon-specific stop words that are clogging up the data and hindering results. Lemmas could also be used to consolidate words to their root word to improve model performance so that the models aren't held up on words like model and models. The models themselves can be improved, particularly the topic model, as we believe that having that improved will vastly improve the classification model, since the classification model is based off of the topic model results. And then the final improvement possibility is exploring more complex models, like a neural network, which might improve classification performance, but it will take more time. In looking further ahead, increasing the scale of the system is possible by increasing the pull limit of the keywords so that there are more articles pulled. Additionally, different or just more keywords can be utilized to better serve other purposes or just have a more broad knowledge base. Hey, thank you for your time. We look forward to working together. We utilized a lot of knowledge gained from the blueprints for text analysis using Python, machine learning-based solutions for common real-world applications by Albrecht and Winkler.